No, it's just, this one works fine. I want to do two of them for a test, but I don't really need it. So let's go ahead. We're trying to make photons interact with each other and use that to make materials, right? So where did we finish our story? It's aligned now. Great. Okay. So where did we finish the story yesterday? Well, we said a material is made up of a bunch of particles, right? Particles meaning that they have some dispersion relation that relates their energy to their momentum. And the particles interact with each other. We need some attraction and repulsion. We need to be able to make traps in magnetic fields. And then they can order and do exotic interesting things, right? So yesterday I told you in several different systems how to make photons act like particles. We talked about how to make optical photons act like particles in the continuum, and how to make microwave photons hop between lattice sites and act like particles in a lattice. What we're going to talk about today is how to make them interact with each other and order. So let's get to it. There's a bit at the beginning of an introduction on what we mean by strong interactions. Okay? The essential challenge for photons is that they naturally do not interact with each other. If I take two laser pointers, you can see this red one here and this green one here. What happens when the beams cross? Yeah, yes, I have. Have you guys all seen the original Ghostbusters? Streams is what he says, not dreams. Right? But in any event, as you can see, nothing happens as these beams cross, right? Because we don't live in the Star Wars universe for the most part. So the challenge is to make our photons interact with atoms, and the atoms then interact with each other, okay, and have that atomic interaction back act on the photons. And so what we'll need to figure out is how strong do the interactions between the atoms need to be, and how strong does the coupling between the light and the atoms need to be. And this is what's called this cooperativity scaling. And then I'll talk to you about building materials in both the optical and microwave photon platforms. Okay, so let's hop right in and talk about how to make photons collide. And we'll start with how electrons collide. Well, fundamentally, if you have two electrons approaching each other, they exchange a photon, right? And that photon carries momentum. And the electrons then go back out, having undergone a collision. Okay? So you might say, this is the simplest Feynman diagram there. Let's just turn that on its head. Two photons come in. They exchange an electron, and then two photons go back out. This is not allowed for a variety of reasons, the simplest of which is conservation of charge, right? Photons are uncharged, so I can create a photon out of a vacuum, no problem, right? I can't create an electron out of a vacuum like this. What I can do is draw a diagram like this. Two photons come in. One of them emits an electron-positron pair. The other one absorbs it and then emits its own electron-positron pair, and then the two photons go back out. So this is allowed, but fundamentally the challenge is these photons can have any energy down to zero, right? Because a photon, its energy is just the frequency times Planck's constant, right? So as I go to lower and lower energies, these wavelengths just get longer and longer. Fundamentally, I can't create an electron with less than 511 keV of energy, right? So as a consequence, if this photon came in with much less than 511 keV of energy, right, this process is very off resonance. I've had to borrow a lot of energy from the vacuum to do this. So this is allowed, but if you compute the cross-section for this process, it's extremely small. So, just as a starting point, does everyone have a physical intuition for cross-section? Does anyone not have a physical intuition for cross-section? Does anyone need more coffee? Okay, so let's sides of this for a reason. All right, let's use the force. There we go. Okay, so the picture you should have for a cross-section is essentially how big the object is. Okay, so what I have in mind is I have a particle here that's coming towards another particle, and the question is, how close does it need to be to that particle to collide with it? Okay, so the simplest picture that you should have in mind is if this picture has a cross-sectional area of A, or a cross-section of A. Well, this is a not good marker. This is a trash bin. If this particle over here has a cross-sectional area of A, okay, so we say sigma is equal to A, then if this other particle is within that cross-sectional area A, okay, it will hit and scatter. So if I tell you that for a visible photon, you know, the wavelength of half a micron, the cross-section for two photons to scatter off of each other is 10 to the negative 56 microns squared. Okay? What that tells you is that the radius of this interval is about 10 to the minus 27 microns. Okay? So that means the photons need to get very, very close to each other. Or you would need to have a tremendously large number of photons for them to collide. Okay? All right, so let's put this back together. Okay. Great. All right, so how do we get around this fundamentally? Well, the essential point is that this intermediate state is very, we call it off-shell or off-resonance. We've had to create particles out of the vacuum, and we don't have the energy to do it. So, but the idea is good. The idea is the photons interact with electrons, the electrons sort of interact with each other, and that turns back into photons, and that gives us our photon-photon scattering. What we need is some kind of excitation that essentially costs us zero energy. Okay? So, instead of using electrons, we'll use atomic excitations. We will absorb the photon, okay, with an atom which is resonant. We'll let the atoms interact with each other, and then re-emit the photons, okay? And this will give us our collision. So what we'll come to, probably like 20, 25 minutes, is a cross-section of 100 microns squared for an optical photon, okay? And so what this means is that when this first photon comes in and tries to collide with the second one, well, the second photon now looks like it has a radius of like 5 to 7 microns. Okay, so it's for those of you with finer hair, okay, this is a photon whose size is about the diameter of one of your, or half of one of your ears, which is quite a large object. Okay, so the essential story here then is that we want to make photons interact with each other by converting them from light to matter and back to light. So the first question that you want to ask yourself is, how does this process work? Well, how does the light to matter conversion process itself work? The essential size of an atom for absorbing a photon is given by the wavelength of the resonant transition of the atom at most. Okay? So if we're talking about visible light, if the atom has a transition at say 500 nanometers, you can more or less think of this atom as being about 500 nanometers by 500 nanometers when you shine light at it, which is right on that resonance. Okay? So now we're going to imagine a photon goes past the atom, and the wave packet of that photon is going to have a transverse size of W. Okay? So that means that the probability that the atom absorbs the light, which is more or less equal to the probability that the atom re-emits the light into that same direction, is given by lambda squared divided by the wave squared. Okay? And generically, you know, focusing photons down to this kind of a small size is quite difficult, so this number will be small compared to unity. All right? So if we have only one atom, the interesting thing is that this atom only absorbs this photon with some small probability, but it's a very nonlinear object. What do I mean by nonlinear? Well, once it has absorbed one photon, it can't absorb another. So this is an example of a way to make photons interact with each other, right? If I send two photons past an atom, if the atom absorbs the first one, then the second one goes through, right? And if the atom absorbs the second one, then the first one goes through. And you can see that this is kind of a collision between the photons. If the atom weren't there, then they both just go through. So this is sort of a minimal example of something that would provide a collision. But the challenge is that this probability of a light-matter collision is very small, right? Because of this lambda squared over weight squared. Okay? So maybe you say, well, I've got a good solution to that. Let's just put a whole bunch of atoms there. Okay? And that substantially increases the probability that your atoms absorb your light. Right? What's the problem? Well, the problem is, once one of those atoms has absorbed a photon, there are still, you know, if there were 1 million atoms to start with, there are still 999,999 left that can absorb the second photon. So basically, the response at the medium is not nonlinear, right? And so this does not really give you interactions between the photons. Okay? So, how do we make this work better? Well, there are a couple things you can do. One is, you take a single atom, okay, and you put it between a pair of mirrors. And as you may remember from yesterday, I really like mirrors. Okay? So the point is, each time this photon goes past the atom, the size of the light is W. The probability that it gets scattered each time is lambda over W squared, but it gets a whole bunch of chances, right? Given by basically the probability that if the light is lost on a given pass with a probability epsilon, I have more or less a factor of 1 over epsilon here, and I call this the finesse, right? So a typical optical cavity will have a finesse from 100 to 100,000 or a million. Right? So I can get a big numerical factor improvement here from that. And so this is the regime of circuit or cavity quantum electrodynamics. Right? It's basically this idea that you get an enhancement in your light-matter interaction from the number of round trips of the light between the mirrors. Okay, but it's a little unpleasant here, because now you have to trap this one atom, if it's a cold atom, between the mirrors. And for many body physics, now maybe you want to have a bunch of cavities, each with one atom in it. And so we'll come back to these ideas shortly, but let's talk about another possibility. Another possibility is to actually have the atoms directly interact with one another. That's what we started with, right? So how does this idea work? The idea is, my first photon comes in, and I have a whole bunch of atoms here. Okay? So this whole bunch of atoms means that with high probability, one of them will absorb my photon. Okay? And then I want to have another photon come in. And the key is that once one of these atoms has absorbed my light, the atoms can talk to each other. And somehow we make them agree that once one of them has absorbed a photon, the other ones all turn off their absorption. Okay? Due to just direct interactions between the atoms. Okay, and then the second photon doesn't see atoms and just goes through. And so I haven't really told you how to implement that, and we'll come to that shortly. But this is the regime of Rydberg electromagnetically induced transparency. And then the last possibility is to combine these two for really strong interactions. So have atoms that interact with each other and put them inside of a cavity. Okay, and now you get many, many, many collisions. within, or very high probability that the photons collide with each other, if you prefer. Okay? And now, let me just also say, in terms of drawing parallels, the regime that works well for synthetic quantum materials here, that is to say, the regime in which the system can tell the difference between 0 and 1 and 2 photons, that they collide with each other with high probability, is precisely the regime of quantum computing, right? You need nonlinear systems that can tell the difference between 0 and 1 and 2 excitations, okay? And coupling those systems together allows you to develop entanglement for building a quantum computer, or develop entanglement for understanding material properties, right? So it is no coincidence that the same sorts of systems that are used for exploring synthetic quantum materials are also used for exploring quantum many-body physics, okay? All right.
So I didn't understand how using atoms and integrity doesn't do an overhead compared to atoms because we have a high capacity. So can you show me?
You're saying
the second one and the third one?
So how do we get from here to there?
No. Like how does the collision probability
Why does it stay high?
No, why didn't it change? Like it's still one.
So it's a little weird to think about this. Essentially, in practice, there are technical limits here depending on how strongly your atoms interact with each other. Okay, so one can easily work in a limit that basically you use atoms that have very strong interactions between one another. Okay, and so whether they're in free space or in a cavity ends up not mattering that much because they interact so strongly. Basically, the probability that once the excitation gets absorbed, the atoms see each other can be basically 1.
Okay, so I can think of this, like I think they're repaired atoms.
Yes.
And once you excite them, you create a repair radius.
Yes.
And no matter how high the impedance is, when another photon comes, it doesn't matter because it's within the repair radius.
It's within the blockade radius. So this is the hand-wavy kind of story, right? But what I'm trying to say is that there are essentially 2 different things that you need for making materials out of light, right? One is that the photons need to be mapped into the matter, right? And the other is that the matter needs to interact very strongly, right? And essentially the point is that if you don't have both of those things, you can have one atom and the matter interacts infinitely strongly, right? That one atom can only be excited once. Great. But it probably doesn't absorb your photon with high probability. So it's not very useful, right? On the other hand, you can absorb a photon with very high probability, but if the system's not nonlinear, then you don't get collisions. So let me bring this back to quantum computing for you just for a moment. If you have a quantum computer, so what are the ingredients that you need there? You need to be able to control the states of your individual qubits and potentially even map quantum information in and out of your system, right? And you also need nonlinear objects to implement your gates, right? And so the point is, if you try to use a single atom as your quantum computer, well, it can be very hard to efficiently map the information in and out. Say you want to send information from here across the country, you want to map it out as a photon. Well, you may be able to do all of your computation in the atom, but you can't map it out efficiently, right? And so there are these 2 things that you sort of have to get at the same time, and they're not controlled by the same figure of merit, is sort of my point. These are not entirely orthogonal figures of merit, but almost orthogonal. Okay, so let's, oh, I pressed the wrong button. Sorry. Yes?
So if I already try to connect this to what you explained the last lesson, where I see a difference is if you use this finesse argument, you are working on the time scale of a decay of a flutter. How possible is it that in the lifetime of this photon it interacts?
Yes.
With the atom? But then in the other picture, if I have no cavity, I have a single possibility that they interact with each other and it happens, for
it does.
Yeah, that's true, right? But that means that this argument only holds if I want to ask do my photons interact in their lifetime, but isn't your physics happening in and around?
No, my physics happens, well, it's an interesting question. Fundamentally, the answer is no. The physics is not happening in a round trip. Because remember, the point is we're talking about, and this is again getting a little technical, a single longitudinal manifold of the cavity. Yes? So that means that we're kind of coarse graining over many round trips. And then you see that over many round trips you get these are your two mirrors, over many round trips you get transverse dynamics of the photon. So the point is, in the cavity, very little happens actually within one round trip. If a lot of stuff happened within one round trip, you'd be using many different longitudinal modes of the cavity, which is another interesting regime, right? And people do think about that. That's what's called typically the ultra-strong coupling regime, right? And Andrew Haug is studying that with circuit QED. But it's a different regime than we're talking about here. Okay, but what's the fundamental point here? The probability that a single atom absorbs a single photon of size W going past it is what I call the single particle cooperativity. And there's this extra factor of 6 over 4 pi squared, because it turns out the cross-section of the atom isn't lambda squared, it's lambda bar squared, more or less. But essentially, this is the probability that an atom absorbs a photon that goes past it, okay? If we have a cavity, we get an enhancement by the finesse of the cavity, okay? And it turns out that this is equivalent to the light matter coupling strength G squared divided by the cavity line width times the atomic line width. Okay? So for those of you who like to think about Jaynes-Cummings physics in this quantum picture, right? You think about G, kappa, and gamma. But what I'm telling you is that there's a very physical, geometrical interpretation. Did I make any statement about how long my cavity was here? No. Right? I don't care how long the cavity is. Right? The probability that the atom interacts with a photon in the cavity is entirely insensitive to the length of the cavity. It cares only about these geometrical quantities. Okay? So what's the bottom line? For photons whose collisions are mediated by interacting matter, that is to say photons that are absorbed by matter, and then the matter interacts and it's mapped back to photons. Okay? The probability that any given collision is successful scales with n times the cooperativity, or the square root of that, right? And so once that number gets much larger than unity, essentially the number of collisions that you get before this process fails and the particles don't collide with each other is basically the square root of the number of atoms times the single particle cooperativity. Okay? So at a fundamental level, the amount of quantum dynamics that you can get out of a system made of quasi-particles, where the matter part is strongly enough interacting that that collision probability is 1, essentially, is given by the light matter conversion, and this is how much you get. Okay, so the point is, we need very strongly interacting material particles and very strong light matter coupling. How are we doing on time? Not so well. Okay, because this is a review, I would like to give a little context about where the field has been until fairly recently. There's a beautiful review from Jacopo Carosotto and Cristiano Guiti in Reviews of Modern Physics that I suggest everyone take a look at. It's very nice. And this review is mostly about weakly interacting photons. Okay? That is to say, the light matter coupling strength is very large. Okay? So the photons are very efficiently mapped back and forth into matter particles. But the challenge is that the interaction between the matter particles is very weak. Okay? So as photons go past each other, they very rarely collide. So these systems require you to have many, many, many photons to have any kind of substantial interactions, and as a consequence, they kind of act like mean-field fluids. Okay? But it remains the case that one can study superfluidity and Bose-Einstein condensation, acoustic black holes, all sorts of really beautiful, fascinating physics is accessible there in these platforms. What happens when we add to this strong matter-matter interactions? So the point is, the challenge for them is that their photons interact with a medium that is weakly interacting. That is to say, the atomic excitations in the medium are physically small, right? When the photon gets absorbed by an atom, that atom only ends up with a size of about an angstrom, because that's the typical size of an electronic orbital in an atom, right? What we need is atoms that interact with electronic orbitals that are about a micron. Okay, so that's a huge orbital, something in the range of n equals 100 principal quantum number. These atoms are extremely sensitive to everything. They can sense a surface from millimeters away, right, because they're so sensitive to stray fields. You can't have any air or anything else nearby because it just destroys them. So this is where the cold atoms come in. These atoms have to be trapped in a vacuum chamber. But as a consequence, they can have electronic orbitals that are almost a micron across. And this gives us this very strong matter-matter coupling that we need for the science. Okay? So the picture that you should have, sort of fundamentally, and this was pioneered by Misha and Vladen and Charles Clark, Charles Adams, sorry, and others. I suggest these early works. Is that a photon goes into this atomic medium, and light slows down when it's in a medium because it spends some time absorbed by the medium. Okay? And here we're creating a situation where when the photon goes through the medium, it turns into atomic excitations in this very highly excited state. This process is called Rydberg EIT. We need strong light-matter coupling, so we use a strong transition of the atoms, 5s to 5p. But this state has a small electron radius. So then we shine a laser beam that takes any atom that's excited here and just populates it in this very highly excited state. So the point is, the first photon goes through and moves very slowly, but the interesting thing is that once this first photon is in there, if the second photon gets near it, it actually moves much faster. Why does it move much faster? Because it doesn't see this medium at all. The interaction between the electrons basically moves this level off to infinity, and so the medium's gone. And so what you see is an index of refraction for the second photon, which depends upon the distance from the first photon. It acts like a lens. Okay? So the first photon lenses the second photon, and that looks like a collision. Okay? Great. And so the idea is to study this kind of physics, but with a thin atomic cloud between two cavity pairs. That's the kind of work that my group does. Okay? The first demonstration that this could work comes from Vladen Vuletic and Misha Lukin at MIT and Harvard, respectively. The basic aim is to take a cloud of atoms and compress it down to about a 10 micron radius. It's about 60 microns long. And perform this kind of Rydberg EIT experiment where any photon that goes through this cloud excites an atom up to this 100s Rydberg state. Okay? And basically what's observed is that once there's a photon in the medium, if a second photon gets close to it, it's kicked out of the medium. This lensing kind of just fires the photon off at some random angle. So if you take nothing further away from this talk, who knows about G2 correlation functions? Everyone knows about G2s? Almost? Good. Even Norm knows about G2s, and he's playing chess. Okay. So the point is, what they observe is anti-bunching of the light that comes out. A strong suppression, a detection of two photons coming out at the same time. Okay? So the recent experiments from my group start with a magneto-optically trapped gas of atoms, very much like these other experiments, load them into a lattice, and then basically use what we call degenerate Raman sideband cooling to cool and compress this gas into a very thin pancake, because the light's going to propagate in this direction. But as you pointed out, it's very important that the dynamics only happen on many round trips through the cavity. So as a consequence, we need this gas to be thin compared to the interaction range between the electrons. Otherwise, the photons will try to interact with each other in one round trip. We don't want that. We only want transverse interaction. So we compress this cloud down, and then we can perform the same kinds of experiments. For those who are cavity QED experts, when we perform spectroscopy on this system, we see these two vacuum Rabi peaks corresponding to the light matter coupling for the two-level atomic system. And this third electromagnetically induced transparency peak, which is narrow because the Rydberg state is very long-lived. Okay? And this corresponds to photons living in the cavity, but spending most of their time within this 10 micron thick atomic sample as Rydberg excitations. So for scale, this whole cavity has a length of about 6 centimeters. And in these experiments, the photons spend something like 90% of their time within the 10 micron thickness of this atomic cloud. Okay? So now what we expect is if we send one photon in, once it's in there, a second photon can't go into the system. It'll just reflect off. Okay? Until the first photon leaves, and now another photon can enter. And so, again, we can perform these blockade-type measurements and see that the system can only hold one photon at a time. So in a single-mode cavity regime, we would call this a quantum dot, a polaritonic quantum dot, in analogy to the electronic counterpart. Okay, so that's great. With all of that under our belts, the question is, what if we combine the degenerate states of a twisted cavity with strong photon-photon scattering that we've just shown? What do we get? Well, I can show you some preliminary results there, but before we do that, and I think what's actually going to happen here, as I'm looking at the time now, is we will almost certainly spend the whole time today talking about optical photons, and we will spend tomorrow talking about microwave photons. All right, so before we can talk about this, though, we need an experimentalist introduction to the fractional quantum Hall effect. How does that sound? Terrifying? Would you prefer a theorist introduction? Okay, who knows about Chern-Simons theory? I don't even, okay, we got one? Get out. It's because my last name is Simon. He has an extra S on the end, and he's extremely rich. Okay. No, seriously, you know this, right? But he didn't make his money on the fractional quantum Hall. There's no money, as far as I can tell, and Bob Marlin made $1 million, right? Yeah? Do you have a business proposal?
No.
Okay. Are we all awake?
Yeah. Don't know what he decides to be nice. Right.
So I've been thinking, actually, with all of this quantum stuff going on in the US right now, I think what we should start is a topologically protected investment firm. So if anyone would like to invest, I also have a bridge to sell you. Okay, so
He either makes money or loses money.
what? Yes, exactly.
Either makes money or loses.
I mean,
Totally correct.
I make money. That's for certain. Until I go to jail. Okay. So what happens? Norm's embarrassed. I'm not sure why. Go back to your chest. We're 1-1 on this trip. I'll have you know. Okay. So let's take a step back and talk about what happens when you put an electron in a magnetic field. Okay. Well, what do we know? It undergoes these little cyclotron orbits. And the thing that's weird is that this is the Hamiltonian for the system. But because the vector potential has this V0 cross R term, it looks not translationally invariant. Okay? And this is what makes the quantum Hall effect at some level weird to start with. But the thing that we know is if I put an electron in a magnetic field and I translate it over a little bit to the right, I see these same cyclotron orbits. Right? So in some kind of a physical sense, the system is translationally invariant. Okay? So we know that. What else do we know? If I increase the velocity of the particles, the orbital frequency stays the same. Okay? So what does this kind of tell us in terms of the quantum mechanics? Well, it's going to tell us that we're going to get some essentially translationally invariant manifold of states at each energy. And the allowed energies are going to be spaced by precisely h bar times this rotation frequency. And that's all that there can be. Okay? So as you may recall from yesterday, this set of states at some given energy is called the Landau level, and the spacing between them is called the cyclotron.
So I'm kind of confused.
Yes.
So this translational invariance is only it's only valid for this Landau gauge, right?
So I'm trying to avoid saying anything about gauges.
But you did.
Yes. So, but this picture of the dynamics is gauge invariant. Can we agree on that? No matter what gauge you pick, you get cyclotron orbits.
I'm not sure.
The cyclotron orbit is a physical particle going in a circle.
Yeah, like cyclotron motion is sure, but I didn't understand the translational information.
So I think what I mean in some physical sense is that the dynamics are translationally invariant. So as a consequence, if you can get the same physics at all of these locations, there's going to be a family of eigenstates that kind of look the same. They will not, I agree, they differ by a magnetic translation operator, mathematically. But what I'm saying is that if I can see the same physics in a bunch of different locations, I have to have some set of states living at the same energy in each of those places.
I think so what you say is like, don't look at the Hamiltonian, but just like look at the particle.
Just look at what happens physically.
Take it there and then look at it there.
So the point is, and I was saying exactly what we're struggling with here. This math makes it look not translationally invariant. And there is this whole issue of gauges that we're going to struggle with a bit in a moment, right? But physically, we can see that there have to be Landau levels. Okay. Good. So, what happens quantum mechanically? Well, it's what I just said. I forgot what was in my slides. I would say it won't happen again, but it will. So great. So we've got these Landau levels. Don't worry, I messed it up before you you asked a good question. So we have these Landau levels, but let's look at these states in the lowest Landau level. Okay? And this was the question that was just asked of me, which is, in this gauge that we've chosen, what are the eigenstates? Well, I told you should think of them as translationally invariant, but it turns out that depending on what gauge you pick for the vector potential, okay, the eigenstates will be different things. And that won't change the dynamics in the system, but it does change how we write down the solutions. So what I would like to do is use this gauge, and then you see that the eigenstates are these rings. We saw them yesterday in the data, right? And the point is that the rings are states of definite angular momentum. And the thing that's worth noting is that there's a beautiful way to write down these eigenstates. Okay? You can write the eigenstate with angular momentum L as z to the L times e to the minus magnitude of z squared. So what is magnitude of z squared? It's r squared. Okay? And z here is x plus iy. Okay? So you can think of this as r to the L, e to the I L theta, times e to the minus r squared. Okay? So the amount of phase I get going around a ring with angular momentum L, I knew there was a reason that we had another point here, is 2 pi times L. Okay, so why is this important? Well, it's important because the next thing that we're going to do is add interactions between these particles and ask about what the ground state of the system is. So this looks horrible. Okay? Classically, you've got particles going in circular orbits, bouncing off of each other. Who knows what the heck happens? Norm might know, but I sure as heck don't. But quantum mechanically, it turns out you can write down a very beautiful answer to this problem. Okay? The point is, our challenge is to write down for interactions that are weak enough that they don't promote particles up to this first excited Landau level. We want to put a bunch of particles into this system that all live within the lowest Landau level wave function manifold. That is to say, each particle is one of these wave functions, or some superposition, or some entangled state between the particles. And we want to minimize the interaction energy between the particles. So how do we do that? Well, let's think about what these collisions do. What you discover is that basically if I have a particle in L equals 1 and a particle in L equals 4, well, when they collide with each other, we need to conserve more or less energy and angular momentum. Okay? So we're going to stay within these lowest Landau level wave functions, and to conserve angular momentum, 1 and 4 can go to 2 and 3, or it can go to 0 and 5. And there's some amplitude for each of those processes. And so the point is, we need to find, for n particles in this system, some steady state solution where as they're colliding and permuting between these different states, the wave function doesn't change. Does that sound horrible? It sounds horrible. But we can just write down the answer, it turns out, because Bob Laughlin is a genius. This is the answer. Okay? This is called the Laughlin wave function. So how can we see that this is the answer? Well, the first question was, do all of the states of the individual particles live within this lowest Landau level? You can immediately see that the answer is yes, because, so what I've got here, let's just first summarize this wave function. First, I have out front e to the minus r1 squared times e to the minus r2 squared times e to the minus r3 squared times e for all the particles, right? So that's good. I no longer need any of those e to the minus r squared factors. They're all taken care of here for all the particles. This piece is a product over all I and j, okay, of zi minus zj squared. Okay, so if there were only two particles in the system, this would just be z1 minus z2 squared, where z1 is the position of the first photon in this case, and z2 is the position of the second photon. So, what are the terms that we would get out? We would get z1 squared, z2 to the 0, right? z2 squared, z1 to the 0, and 2z1, z2, right? Is it clear that each of those consists of single particle wave functions in the lowest Landau level? Is that unclear to anyone? Is it clear to anyone? Who doesn't care and wants me to just move forward? Okay, if you don't raise your hand for any of the three, I'm going to assume it's that. Okay, so the basic point is that if I have z1 squared e to the minus magnitude z1 squared, that's a particle, but that means particle 1 has 2 units of angular momentum. But remember, that's multiplied by z2 to the 0, e to the minus magnitude of z2 squared. So that means the other particle has 0 units of angular momentum. Okay? And so the point is, the total two-particle wave function has each particle within the lowest Landau level. But now, what about the interactions between these particles? This is the cool part. This wave function goes to 0 whenever the particles are in the same location. Right? So that means I pay no interaction energy. Right? So there actually can't be a state in some physical sense. Before someone starts telling me about higher order Haldane pseudopotentials, someone like Norm, just know that I don't care. Okay? If someone who paid for the winter school has questions about that, I'm happy to answer. Trolls are going to troll. Okay, great. So the point is, this is a zero energy state for this system. That wasn't recorded, but. Wait for the third ball there. So in solid state systems, the signatures of making this kind of state are these fractionally quantized Hall conductance plateaus. Basically, you measure transport and see some very bizarre stuff. But so one could think about trying to make measurements like that in synthetic many-body systems. But to me, the fundamentally neat thing about the synthetic systems is that often the things that are easy with solid-state platforms are hard here, and vice versa. Now, of course, it's never a good thing that the things that are easy in solid-state are hard here. But in some sense, it does motivate us to develop new probes of the systems, which tell us different things, and new and important things, I would say, fundamentally, about the properties of these many-body states. And that's where much of the need is, intellectually. Okay? So, you don't really need that slide, but what we do know is that magnetic fields for photons plus photon-photon scattering should give us a topological view to many-body states of light. Okay? So, how would one observe this in the lab? So what I've showed you so far is if I just have this lowest mode, this quantum dot data that I showed you, if I probe through this cavity on the lowest mode, well, if the photons collide with each other, one photon can go in, but due to the repulsion between the photons, the second one can't go in, right? And so this is what we call a single mode blockade effect. It's the simplest interacting physics that I would say one can explore. Okay? So here's where things get interesting. What happens if I probe my cavity instead on this L equals 1 angular momentum mode? Okay? Well, you might say the photons still interact with each other and repel each other, so I can't put two photons into the system. That's what one might naively suspect. But the neat thing is that, in fact, another thing can happen. Once I have two photons in this L equals 1 state, they can collide with each other, and one can go to L equals 0 and the other can go to L equals 2, right? That conserves both energy and angular momentum. And then once they're in 0 and 2, that has some interaction energy, and they can also collide and go back. So, physically the point is, we are used to interactions in a cold atom scenario just being, for a given eigenstate of the system, a shift in the energy, right? But the point is that because the interactions are not, in a mathematical sense, diagonal in the basis of the angular momentum states, okay, the collisions can take us between pair states. So the question is, for the two states to consider, which are two photons in L equals 1, or a photon in L equals 2 and a photon in L equals 0, what are the two particle eigenstates of that system? Okay? Well, it turns out when you diagonalize that 2 by 2 matrix for the interacting system, one of the eigenstates is two photons here minus the state with one photon here and one photon there. And that state I can factorize as Z1 minus Z2 squared, right? So this state has 0 interaction energy, right? So it's not surprising that that's an eigenstate. But this is now a cool thing because we're now doing quantum optics, but the states that we make are topological few-body states, okay? When I probe on L equals 1, what comes out of my system is two particle Laughlin states, right? At least in this version of the system that exists in my mind, right? So this idea originally came from Jacopo Carosotto, and I'm not even going to try. It's a Turkish name. What? Thank you. If you hadn't been here, I would have tried. But you mean Umakalawar? That's it. Has it? Oh, really? Okay. My apologies. Anyway, this guy's great. Jacopo's great. They proposed this idea. And what I would like to do is show you brand new data in the waning moments here of this happening. So, there's not actually, so this data was collected, I think yesterday, or over the weekend, by my graduate students and Logan Clark and my amazing postdoc. Logan's the postdoc and Nathan Shine, who made these twisted cavities. He's a phenomenal graduate student. But they know that I like cats, okay? So they sent me slides with cats and weird cartoons on them, but they sent it as images, so I can't remove them. So this is their humor on the remaining slides, not my humor. I apologize for that. Okay, so our cavity has L equals 0, 3, 6, etc. degenerate. I don't even know this guy. L equals 0, 3, 6 degenerate. So what we're going to do is inject light on L equals 3 and see if these photons convert into L equals 0 and L equals 6 photons. Okay, this would be like a Laughlin state on a cone. The key point here is that this may look like the way a parametric down converter works, but we've also measured blockade in L equals 3, which means that there are never more than 2 L equals 3 photons in the cavity. So this is in a very strongly interactive regime. Okay? So the first signature here is to see that these L equals 0 and 6 photons come out. Okay? So how does the experiment work? We have this twisted cavity. Ignore this comment that says flow K-beam. That's fancier than you need to worry about for now. But the essential game is we have our atomic sample in here to mediate interactions between the photons. We send in an L equals 3 coherent state generated by a digital micromirror device. And we use this electro-optic modulator to tune it exactly to the proper resonant frequency of the cavity. And then we look first for photons in the L equals 0 mode. Okay? And if you see photons in the L equals 0 mode, that's sort of indicative that you've got some interactions going on. And so you can look at this in sort of 2 different regimes. You can make your modes non-degenerate. Notice this is not L equals 3. L equals 6 and 0 have been shifted to the left of L equals 3, so that you can't take 2 photons in L equals 3 and conserve energy by going to 0 and 6. And then we can also have a situation where you can conserve energy. Okay? So, what we see is that as we approach this degeneracy point, we start to put photons into this L equals 0 mode. So that's very nice. And in fact, the rate of putting photons into the L equals 0 mode is strongly nonlinear in the rate in which we excite the system. So what this says is that this is not linear lensing of the light. You can imagine that your atoms just act as a lens and put some of the light into L equals 0. But that would be linear. Hi. We don't know anything about the biosphere. But the fact that we see this nonlinear relationship sort of suggests that we're getting some kind of interactions between the photons. The more interesting thing, though, and this is something which is sort of unique to optical photons, is to start to look for correlations between an L equals 0 photon and an L equals 6 photon. So the question is, how do you deterministically detect L equals 6 photons? Well, this setup, you might say that beam splitter cube is backwards, right? Because that's not how beam splitter cubes work. But actually, this beam splitter cube is forwards. The way the experiments work is all of the light comes out. This cavity transmits all of the L equals 6 photons. So you can think of this object as like a mode sorter. The L equals 6 photons go to our detectors over here. The L equals 3 photons come back. And because they pass through this quarter wave plate twice, they all go to this other detector. But because this is a single mode fiber, the L equals 3 photons are now rejected. So the next step is to add another filter cavity that is only sensitive to the L equals 3 photons. Then you have a full mode sorter, and you can start to really do full state tomography on these states. But the question is, do we see correlations between 0 and 6? And the answer is yes. In this non-energy conserving case, we see nothing. In the energy conserving case, we see about a factor of 50 enhancement. And this is the G2. The point is the data rates here are not so good yet. This is very quick data. The average value of this is 1, as you would expect. But once we do all of the background subtraction that's necessary for these sensitive measurements, we didn't measure it along that regime. But we see very strong correlations between these two. And then the next thing to do is show that there's a correlation, or excuse me, a phase coherence between the 3-3 component and the 0-6 component. And that's really what you need to do to show that you've made not a statistical mixture of 3-3 and 0-6, but a superposition with a minus sign. And the easiest way to do that, actually, is to just make a G2 measurement off-center. Okay? Because the whole point of the Laughlin state is that that superposition of 3,3 and 0,6 minimizes the overlap of the photons with one another, right? To minimize the interaction energy. So the easiest way to measure that phase and show that it's negative is to look off-center at some little dot here. It just shows that you have suppression of 2 photons. So this was going to be the intermission, but I think this is a perfect time to stop for today. This is Emmy again. I told you yesterday that she's alive. I checked last night with Norm. She was still alive. So we're good to go. All right. Other questions? We good? I'm done. Thank you.
You said something yesterday about the number of states that you can have in a Landau level has to do with the size of the wave functions, and that high enough angular momentum states eventually will leak out.
Mm-hmm.
So does that mean if you put more and more photons, they will push each other around and they'll start leaking out at the edge of your how many angular momentum states you can have?
So this is an interesting thing. One way to answer, to rephrase that question, I think, is imagine you wanted to make bigger Laughlin states. How would you do it? And is there an effect where they collide and induce losses at the edge of the system? So the fundamental trick that we can use is that we can use quantum optics kind of games with either changing the energy levels of the Rydbergs or changing the energy levels of the cavity, which works better, to create a situation where before you get to the edge of the mirrors, we change the energy of the higher angular momentum states quite discretely. So you'll have, say, up through L equals 30 are degenerate, and then L equals 33 and above are at a different energy. And that will prevent the particles from leaving, okay? And then in terms of how does one actually assemble a many-particle Laughlin state, the answer is you don't use the spectroscopic techniques that I introduced today. This is kind of the brute force quantum optics extension of single mode physics to few particle physics. What you use is dissipative preparation schemes. And I'm going to introduce you to the dissipative preparation schemes for microwave photons tomorrow. This is basically to engineer a reservoir that you can turn off later that allows you to thermalize it to a target many-body state and then remove it once you've made the state you want. And so you can use those same kinds of techniques to make the optical photon states. And that's where this story is going.
Okay, thank you.
Going back to your last example, actually I could say that this is also connected to quantum depletion in the superfluids, right? They can take 2K cos 0 boson, they scatter to K minus 3K. So what is so special here that they should see? Because I can also have sort of various vortex lattice states, like superfluids,
so this is
level.
So I think the key point is that this physics happens with very few particles in your system, right? It's if I have 2 particles and they collide strongly enough with high enough probability that they go to different states, right? That means I'm in a strongly interacting regime. Let's compare that to a superfluid, right? There, if I just put 2 atoms into the lowest state of my harmonic trap, you don't get any substantial quantum depletion, right? You need many, many, many particles to increase the collision probability sufficiently that they start to go into these other states. So that's why I say it's sort of similar to an optical parametric oscillator in that way.
Well, it's like you spin changing collisions. You start with 0, 0, and you bring it to degeneracy, but then
That's
the
right.
pairs, and you get these entangled.
Yeah.
But we know that, let's say, as we tune interaction, let's say, for particles in Landau level, you have a transition between vortex lattice and a fractional quantum pole state, and like interacting bosons, and for the interacting bosons, you can have pretty strong interaction and still a vortex lattice.
Okay. So we have to be careful. If you want to go back to that picture, you say, I have some number of particles in a trap of some size, right, with some strength of interactions, and then I'm going to turn up the magnetic field, right? So then the question is, and that's a question of essentially, I think, how many fluxes you have per particle, right? And when you have many less than one magnetic flux per particle, you're likely to get kind of a mean field vortex lattice.
It's also a function of interaction. I can fix my vortex length and just change interaction. And then I can go.
So you're saying you
vortex
could
length.
also have a fractional quantum Hall state at, what is it here, you say?
Well, you always need a certain filling fraction, right?
Yes.
But at the same filling fraction, I'm not guaranteed to have a fractional quantum Hall state. I can still have a superfluid phase.
Okay, so then I guess maybe my question is, what is your question?
No, but then because somehow this can be just like strong quantum depletion in what would be like a vortex line.
So, okay, in that sense I agree that fundamentally the smoking gun is showing that you have anti-bunching at all points in space, right? The vortex lattice doesn't actually have that anti-bunching everywhere in space.
Or at least it's weaker probably.
I mean, the G2 essentially doesn't go to zero. You can still have particles at the same location. So, but if you know that you have two particles in your system, right, and that half the time they're in 0,6, and the other half the time they're in 3,3, right, and on top of that, I measure a correlation function anywhere but in the center in space, that measures the relative phase between those two terms. And essentially, does that kind of make sense? But I agree with you that fundamentally what I have shown you is not proof that this is like a two-photon Laughlin molecule until you have that phase as well. We can talk later.
Yeah, I have a short question. So I think there's like, I'm kind of confused. Like, in the last lecture, we had this, our classical harmonic Gaussian modes, and then we started just to kind of became like Newton modes, right? And now, when you show me like the pictures, they kind of seem like the number states in the coherent state indices. So is there like a connection between them? Like these, sorry. Yeah, these like Randall levels exactly seem like, yeah, that's like this slide? This one, yeah, these, they exactly look like number states in the coherent state indices, right? Our Randall levels.
Yeah.
What's the connection between them?
So let's talk about single particle physics, right? There is a sense in which lowest Landau level physics is the same as a quantum harmonic oscillator at the single particle level.
Exactly. Yeah.
Okay.
Without engineers.
Well, let's just talk about a single particle,
Yeah.
right? The essential point is that what are the commutation relations that are essential for having a quantum harmonic oscillator? You need like p squared plus x squared Hamiltonian, and x and p can have some commutator. It turns out in the lowest Landau level, you end up with x and y having a commutator that's
IX commutators or some.
no, x and y,
Yeah.
not px and py, or not x and px. It's x and y. So the point is, we're used to a harmonic oscillator in phase space, where one axis is x and the other axis is px. And then you talk about Fock states being rings in that space. The Landau level, basically the magnetic field mixes x and y with one another. Okay? So now you can think of the eigenstates, the axes in phase space are x and y, right? It's, again, like a one-dimensional system, right? Remember, I only had to index the eigenstates with a single index. I didn't need two, because the other one gives me which Landau level I am, right? And these rings that we're used to as being Fock states, right, are the angular momentum. Is that, sorry guys?
So the computation is the key that uses this one.
Well, or you could say that the winding comes from the Lorentz force, and the Lorentz force maps px into y, right? But we already had a commutation relation between x and px, and so that creates the commutation relation between x and y. And it's not really that to be very precise, x and y don't have that commutator, It's the projectors of x and y onto the lowest lambda level that have a non-zero computation relation. Okay. Good? Circuits next.